He is currently a senior science research specialist at DOST-ASTI. He holds a bachelor's degree in computer science at Mondrian Ora College and a master's degree in electrical engineering at UP Diliman. He's also a PhD student in computer science at the De La Salle University. So his research focus is on artificial intelligence and its applications in various fields. He's also a technical researcher of the Understanding Lightning and Thunderstorms or ULA Project, which he will be talking about in just a while. So Sir Elmer, the floor is yours.
Good afternoon, everyone. Thank you for tuning in. I'm Elmer Peramo, a Senior Science Research Specialist in the DOST-ASTI. And my area of research is like what, Therese, I'm sorry. Thank you, Therese.
True, sir.
And yeah, sorry about that. And yeah, you were saying that my area of research is in artificial intelligence. And for today's webinar, allow me to share with you how AI or machine learning can be used in weather forecasting. So should we wear a jacket or a sandal today? Should we go to the office or work from home? These are some of the everyday questions that might be able to answer with the help of a weather forecast. I'm sure we're all familiar with weather forecaster that we see on TV, within the news program that we watch. See, there are different types of weather forecasting depending on the time horizon. That it can be long term for the things. If you're going to forecast the weather for 2 weeks or more, or from now, and medium term, if forecasting what the weather will be in the next coming days. Longer than that, I think that usually falls in the area of climate prediction or climate modeling. So I think the majority of us will be interested in short-term forecasting, so which extend up to 40 hours. Now, there's a new kid on the block, nowcasting. So weather nowcasting is a very short-term forecasting that ranges between 1 and 6 hours. So these are not hard thresholds, but basically, you know, the idea behind the temporal resolution of the weather forecasting, and I'm sure common sense will dictate that predictability will is dependent on the temporal resolution. I think it would be harder for us to really determine the weather if we're going to predict the weather probably longer than the short-term time horizon. But remember that these forecasts have also spatial limits. So the weather in one place or one locale can be very different in another geographical area. So temporal and spatial resolution play a different, I mean, it's really different if you're going to predict the temporal and the spatial parameters of your prediction is really a consideration for meteorologists. Now, I mentioned meteorologists. You see, meteorology is the science of weather, climate, and other atmospheric phenomena. So weather forecasting is a big part of this science, and accurate time and timely weather has always been the goal of meteorological scientists. So why do we need accurate and timely weather forecasts? I guess we all know the answer to that. I just want to highlight them so that we won't take them for granted. You see, various human activities have always been sensitive to prevailing weather conditions. So people have been trying to predict the weather since the ancient times. When we're faced with dangerous weather conditions like thunderstorms, our decisions between what should and shouldn't do, I think, can often mean the difference between life and death. So weather forecasting plays a very crucial role. And early warning of weather impacts various aspects of human livelihood. It affects our transportation, be it on air, on land, or in sea. For instance, weather forecasting provides decision-making support to reduce traffic accidents and traffic congestions, which completely depend on the sensing and predicting of external environmental factors such as rainfall or air visibility and so on. You see, utility companies and private businesses are also affected by the weather. So would they stock more of what products? I think the future weather conditions will have something to say about that question. Not only the businesses are affected, but also our agriculture, fisheries, and even the military. In our country alone, we are definitely affected by the weather. Located along the typhoon belt in the Pacific, the Philippines is visited by 20, an average of 20 typhoons, or about 5 of which are very destructive and causing lives and properties amounting to billions of pesos. So now that we have established the significance of weather forecasting, you may now probably ask, how do the scientists come up with their predictions? So one of the more common and traditional methods of weather forecasting is the numerical weather prediction. Okay, NWP uses mathematical and physical models of the atmosphere and the oceans to predict the weather based on the current weather conditions. So this is a computerized model given an initial state derived from basing on the data that you have, observations, humidity, wind, wind speed, temperature, atmospheric pressure, etc. You have to generate forecasts on how the weather will evolve into the future. So these models are usually expressed in differential equations and simulations, and they are solved using high performance computers. So, but are there other ways of doing this? Now, the recent hype about artificial intelligence has sparked renewed interest in applying the success of deep learning methods to image recognition, speech recognition, natural language processing, or robotics, strategic games, and now even to the field of meteorology. So a couple of months ago, DeepMind, an AI company owned by Google, has developed a new machine learning model that can accurately forecast whether or not it will rain into the following future. So this is called precipitation nowcasting. So basically what they did, they have radar images of the atmosphere, and then they use what is called a generative adversarial network. It's a deep learning model to predict what would be the next outcome or the next possible scenarios. Okay, so that's actually how they were able to get a very accurate prediction, and it's been validated by 50 UK meteorologists. Now, before I delve in further, let's define terms I mentioned here: AI, deep learning, and machine learning. So AI is the development of system that mimics or simulates human intelligence, perception, language, understanding, cognition, reasoning, and all. So basically, it's a development of how does the human actually human intelligence is being mimicked by machines, no? So, but you see that AI, most of the AI that we've been hearing nowadays, okay, much of the technology is actually machine learning. Okay, machine learning is that area of AI that allows decision makers to gain more insight from data. So this is more data-driven. This is a data-driven part of AI. So the application of machine learning is varied, and this includes weather forecasting. And actually, there's a growing trend in the sciences wherein, like for example, in the area of physics, in the area of chemistry, they are now going, before we know them to be experimental or empirical, but the next paradigm would be the data-driven paradigm. They are now jumping into the bandwagon of using AI and machine learning in their fields, in physics, in chemistry, now in the area of meteorology. Okay, so there's a valuable opportunity to use machine learning to obtain more concise and in-depth information from available data, including weather data. There are two types of machine learning. One is supervised and the other one is unsupervised learning. The primary goal of supervised learning is to learn how to predict group or a value from past data. So by another definition, supervised learning is a machine learning task of inferring function from a labeled training data. The keyword here is labeled, okay? Now, unsupervised learning tries to identify patterns in data sets containing data points that are unlabeled. So it does this inherently, and basically you're just trying to detect patterns inherent in the distribution of the data, and clustering is an example of unsupervised learning. It can also be used to analyze your data set or before doing a supervised learning approach. So majority of machine learning uses supervised learning. So here's how it works. So you have labeled observations from, for example, in our case, we collect a lot of data from sensors, from satellite images, from radar images, for example, and then data from those sources, okay, are collected, or they are cleaned, and then they are split into training and test sets. And basically, they are transformed to a more structured form so that they can be fed into a machine learning algorithm. And then the output of that algorithm is a predictive model that can be improved using the test set. Okay. Once tested, the model can now be deployed to be used for predictions on new data set. There are different approaches to supervised learning. One is what we call classification. So one is to predict a value or example, predicting, and one is regression, and the other one is classification. So for regression, this one is, we're going to predict an exact value, predicting, for example, predicting the temperature, or another example is predicting the wind speed or the amount of rain in millimeter. Now, these predictions can be, yes, like I mentioned, a numeric value from a continuous interval of real numbers. We call this method regression. Now, it can be applied to time series data. These data are a collection of quantities. When we say time series, they are quantities that are assembled over regular intervals in time and ordered chronologically. And basically, most often they are numeric data ordered in time. Now, the other approach to supervised learning involves predicting a group or an outcome from a discrete classes. For example, if you want to predict whether it will rain or not, so that's an example. That's a binary classification. Or predicting the intensity of the storm according to conventional categories. We have signal number 1, signal number 2, or signal number 3, or signal number 4. So basically, that's classification. Now there's this another workhorse of machine learning is called deep learning. Deep learning, also called representation learning or hierarchical representation learning, is an area of machine learning that heavily relies on artificial neural networks. So artificial neural network, just think of it as just one of those algorithms present in machine learning. But this basically is, I think, based on experience, no, this is more powerful and more accurate, and given given that if you feed it with a lot of data, I think most of the time this has proven to be more accurate than the other machine learning algorithms. Now, it relies heavily on the artificial neural networks and inspired by the structure and function of the brain. There are 3 layers of the neurons in the neural network. You have the input layer, where data is actually encoded, and then the hidden layers where data are being processed, and then you have the output layer where the result will be outputted, and based on the result, you will have your predictions. Okay, so basically, your data input are being weighted and aggregated, and the result of this aggregation is transformed by an activation function to make sure that we also accommodate the nonlinear scenarios. There's an iterative mechanism on how weights are being adjusted based on the inherent pattern in the data. So there's an algorithm that actually configure what weights will you apply for each of the data sets, so that you will be able to come up with a better prediction. And the graph above, the graph there, as you can see, machine learning versus deep learning. That graph above highlights the scalability of deep learning, indicating that the results get better with more data as compared to machine learning. So if you're going to use deep learning, make sure that you have a lot of data that you can use. However, deep learning would require more computing power as well. Speaking of computing power, we in DOST-ASTI have enough computing power to do deep learning research through the core infrastructure or the computing and archiving research environment installed in ASTI. So as a matter of fact, we have applied deep learning in this particular research, and this research actually uses convolutional neural networks, also a deep learning architecture. And basically, CNN or convolutional neural network works well with images. Okay, and what we did here is basically we have converted the time series data that we collected using the weather stations that we have deployed all over the country, and converted those time series into images, okay, using what we call a recurrence plot. But there are many other ways of converting those time series images to those time series into images. We just chose in this research to use recurrence plot. And when we have collected enough of those images, these images representing different weather parameters, basically we stack them together and we fed them into a deep learning neural network. And the output would either be one of the color-coded combination, color-coded output of the rainfall advisory, red warning, orange warning, yellow warning. So this, and also white, which means there's no rain. Okay, so this is a fourfold classification task that we did here, and the experimental results in this classification task yields a 96.27% accuracy. So this one is, we did deep learning for the precipitation forecasting, or forecasting whether it will have a red warning, orange warning, yellow warning, or will have no rain in the coming 6 or 24 hours. Okay, and actually, that research is part of the ULA project, or Understanding Lightning and Thunderstorm, which I will now be discussing. Okay, the project aims to observe the country's weather behaviors through studying torrential rainfall and thunderstorm occurrences as parameters, eventually to enable short-term forecasts. So that's one of our main goals. And it is actually a collaboration between ASTI, the UP Institute of Environmental Science and Meteorology, or UPIESM. Of course, we have ASA on board, the weather authority of the country, and we are being helped, assisted and supported by the professors from the Hokkaido University with our research. And this project is also supported by the Japan International Cooperation Agency, or JICA. And there have been research studies that analyze lightning activity and the relationship between lightning and the rate of maximum sustained winds or intensity of the typhoon. Okay, so this is one of the motivations of the project. This is one of the impetus why that project has been actually conceptualized. Because there have been research from before, like for example, this one from Price et al., that there is really a strong relationship. If there's a lot of activity, a lightning activity, and a typhoon will actually follow, or a maximum sustained winds will actually follow the presence of lightning activities. So what are the goals of the ULA project? So it has 4 main goals. One is to establish the dense and nationwide lightning systems. And then 2 is to establish a 3D satellite monitoring system. and then develop algorithms for forecasting. Most of these algorithms will utilize machine learning, and establish data sharing for related agencies in disaster risk reduction. So this is a very important goal. We should be able to involve stakeholders and other government agencies and share data with them so that they be able to come up with better advisories. For the dense lightning system, we have stations being deployed in NCR, Cavite, and Rizal. So basically, these are we use plate sensor to detect lightning in this system, and it also has other weather parameters, weather sensors involved for collecting other weather data, rain gauge, and collecting rainfall data. Basically, we already have deployed 34 out of 50 deployed stations. One of the reasons why it's taken so long because of the pandemic. I think if the pandemic did not happen, I think this we have somehow reached. We have already probably deployed 50 stations already within Metro Manila. So this is a dense lightning system. This is more the type of crowded or more close to each other weather sensors. But we also have the nationwide lightning system. So stations being deployed, 10 selected Pag-asa regional offices nationwide. And then it uses VLF antenna to detect lightning. So VLF sensors frequency range, it has a frequency range between 1 and 40 kilohertz to measure the electric field radiated from lightning discharges, and are distributed 100 kilometers apart. So these are long distances. Okay, this is not the dense lightning system that I've shown you earlier. Additionally, slow antenna and electric field mill are also installed to detect electric field change by lightning discharge. It also has automated weather sensor and rain gauge for collecting rainfall data. And the status of this system, we have already deployed 6 or installed 6 out of the planned 10 stations. Okay, now I call this the confluence of data. So you can see here, as I mentioned before, we have installed weather sensors all over the country. Aside from that, we also collect satellite images based on the ground receiving from the ground receiving station of the, for example, the Diwata satellites, and then couple that with other data sets, and we house them in a data server in ASTI, in the computing and archiving research environment. And currently, the ULA team is now developing a data processing system for those data sets so that we can provide the public with visualizations and end user API. Okay, these are sample screenshots for the rainfall and temperature data on the ULA Project data viewer. This is part of the ULA application that we're currently developing. We also maintain a website containing all the sensor data that we collect for anyone interested in working on these data sets. This is the Field Sensors website. I'm going to show the link later after my presentation. And yeah, as a research development institute, we do a lot of research and development. This one is actually a research collaboration between ASTI, IESM, and Japanese scientists from the Hokkaido universities. And this one is a 3D cloud reconstruction. So there's a research about the development of effective observation methods through comparing 3D structures of thunderclouds using satellite images. So the images with lightning and precipitation data coupled with the Diwata satellites images, so nag-create sila ng 3D reconstruction of the clouds. Kasi yung cloud, kasi it's a very important predictor ng typhoon, no? Yung cloud, lalong-lalo na kapag mataas yung height ng cloud. So basically, yon. But the thing is, with just the images, okay, 2D lang siya, mahirap malaman talaga kung gaano kataas yung height ng cloud. So what they did some research, and they come up with a 3D reconstruction technique, a very, very accurate compared to other researches. So very, very accurate yung 3D reconstruction technique nila, and this has proved very useful. And also, lightning activities were reported coming from the Pasig area. So we also have some who have validated our research based on testimonials and news reports. So, based from the data that we collected and the result of our research, they are somehow validated by news reports and sightings, including the increase of lightning activities, for example, for a particular event, for example, like in Taal volcano eruption, during that time in January, madaming mga instances ng lightning activity in a certain area, and it was validated naman by the data that we have collected. And so thunderstorm tracking is now possible using the dense network that we have deployed and our artificial intelligence that we're currently studying, and of course the skills from the researchers working on this project. So ipapakilala ko lang sa inyo yung team. So ito yung isa sa part ng team ito. Actually, we went to Tanay in one of the Pag-asa stations in Tanay for our Radioson campaign. Yung Radioson kasi basically yung nasa right. So ikinakabit siya dun sa weather balloon na nasa left. Tapos yan yung part ng mga ulat team. And ito yung mga links naman for if you're interested to actually acquire the data or read more about the activities or the initiatives that we have been doing for the project. And I think that's it. Thank you for listening. I just hope that I have encouraged and inspired everyone to be interested enough to explore more on this topic. Sorry, medyo short lang, pero the objective here is you get to be inspired and somehow informed, and then interested enough to explore more on the topic that I've just discussed. I think that is all. Thank you very much.